Yeah, so the talk was announced, more than a year ago to be about detecting electron pairs in tunneling in lanthanum strontium copper oxide system, which I will cover today, but I will also introduce another work that we've published since on the overdoped side of these materials and done in with magnetic scanning squid technique. So for the first part, this work on detecting Cooper pairs in the noise spectra of the Josephson junctions was done in a relatively big collaboration. Of course, the samples were grown by the MBE technique by Ivan. And then many or most of the measurements, transport measurements, the tunneling measurements were done by the Rice University, the group of Doug Natelson, and his student Pan Joe. And so we've done tunneling spectroscopy at lower temperatures as well as high temperatures in a dilution refrigerator at UConn. And so this work was supported by many agencies. They are listed here. So the devices we're talking about here are LSCO, so lanthanum strontium copper oxide, doped at different levels from underdoped to optimally doped. Then they are separated by lanthanum copper oxide layer, which is undoped, of 1.5 unit cell thickness, and then another electrode of the same kind as the bottom electrode. And so then they were patterned into Josephson junctions that are 20, let's say 20 micron diameter circles with leads deposited on top and also contacting the bottom part of the electron. So these are C-axis tunneling devices. So the current goes through the insulating layer this way. These are MBE grown samples. They are as perfect as they can be. The interlayer diffusion was primarily ruled out by electron microscopy techniques, and we actually know that these devices are not these layers actually don't carry critical current. So the typical tunneling spectra are shown here. You see this is a normalized conductance. Normalized means they were symmetrized and also some background was removed. And so they show that, there are coherence peaks at the right or expected value for the gap, but there are always some states in the gap, and they never show critical current down to dilution refrigerator temperatures. So basically, these layers are quite insulating, which was, I guess, to some extent a surprise, but also it actually played in a good way for us because the high resistance of these layers somewhat enables to see noise in the tunneling current better. So we've measured, basically, you look at the current and you measure, autocorrelation on the current, and that's your electronic noise. And here I'm showing data from underdoped samples. So starting from 70 Kelvin, you see there is a dashed red line that is essentially a model for a resistor noise. And it follows the same, follows the data pretty well. But as you go to lower temperatures, you start seeing this axis noise in the data as compared to the expectation from a simple resistor model. And that noise gets higher at low temperatures, but the surprising part is that it actually is present at temperatures that are even higher than the bulk critical temperature of the leads themselves, right? So the leads critical temperature was measured separately. And so you can see this difference between the expected and the measured amount of noise, and there's clearly a lot more going on in the data compared to the expectation. So this is a data set that I like to look at, and just to guide you, if you go to the paper, this is actually sort of in the supplementary material, but I like this picture most because it shows you that, for example, at the optimal level, x equals 15, 0.15, you see this additional noise at lower temperatures. But then also, if you go to temperatures like 50 Kelvin and even above, you still see the noise. So this is not just some inclusions that may have slightly higher critical temperature. These are really additional noise features that extend beyond the critical temperature. So this, of course, and so you can quantify that by fitting the data to a model that has, this is the simplest one that we could come up with, that has the single electrons component and the paired electrons component. And then this Z factor is a fitting parameter that can tell you how many, in terms of the percent of Cooper pairs you have tunneling. Well, they may be not exactly Cooper pairs, but pairs that exactly tunnel through this barrier. And so then you can have this color scale where the blue color means you have these paired charge carriers. And so again, in the underload side, this is kind of the pseudo gap region, but even in the almost pretty much optimally doped region, you still have this blue color, which is some pairs seem to be persistent even above the critical temperature. So this is really quite a direct finding, and maybe one of the few works that directly show this scenario of preformed Cooper pairs type of scenario for cuprates. And so this is the big surprise. But as I said, it's been a couple of years since then, and we've done. Meanwhile, we've done some. We've published this additional work on focusing on the tunneling spectra. And as I said, the tunneling spectra is very unusual. We've had a relatively some model in this work, and it doesn't capture many features of the tunneling spectra, such as the simplest one, which is the maximum violation of Ambiorga-Baratov relationship, meaning the vanishing critical current. So the tunneling spectra, as well as of course the Cooper pairs, still pose like a challenge for, I would say, for a theory, or something that we would love to talk about if theorists have some ideas as to how to more accurately, for example, model the tunneling spectra. So this is my first half of the talk, and so for the next half of the talk, I'm going to focus on scanning squid experiments on the very much overdoped lanthanum strontium copper oxide samples. So now these are not devices; these are very large 1 centimeter films that are 10 or so nanometers thick. I'm sorry?
We have a problem with the projector, so the light is a problem with is it here? We have a problem in the room. It's nothing to do with you. We can see it.
Should I continue?
It's a projector. Yeah, I think you can. We just hope it will recover. Okay, it's okay. Okay, keep going, keep going.
All right. How am I doing with time? I have more than 10 minutes.
You're doing fine.
All right. So this part is on the overdoped samples. Like I said, this is published in the PRB. This PRB here. The motivation for this work comes from the 2016 Nature paper by Ivan, where they showed that the superfluid density or superfluid stiffness on the overdoped side, quite surprisingly, follows pretty much a linear dependence. And this falls out. This is not described by obviously the BCS theory, but also in general is hard to describe theoretically. So some of these sort of questions were, well, what if you have a film that is non-uniform and this superfluid stiffness on a millimeter scale, which is what Ivan uses as a mutual inductance technique? What if you have some non-uniformity that averages out to this kind of linear dependence? And so this is what we were after to probe with the scanning squid technique. That is essentially a mutual inductance technique, but on a micron scale. So we have this squid, which is a superconducting quantum interference device. It has a a central pickup coil of a few microns, a field coil, also a 10 micron or so. Then it is mounted above the sample, and the sample is being scanned by the piezo mechanism. And so now you can probe different locations and even image the superfluid density in this squid microscope. So these sensors, just to kind of advertise my sort of lab, these sensors are quite unique. They can be small, they can be large, but one of the unique parts is that this mutual inductance, the coil is quite unique. And also the circuit is linearized, so we can actually do very precise quantitative measurements. And that's really what enables us to do this high precision, superfluid density imaging and measurements. This is housed in a 4 Kelvin cryostat that is a closed cycle system. Everything is, except for the cryostat, is built at Connecticut, including the sensors. We also sort of collaborate with Cornell, Stanford, Bar-Ilan, and other universities, and then we have designs of all kinds of squids and kind of extending the capabilities in all kinds of directions. And also, as a capability slide, we also have a dilution refrigerator, which we customize to have no external and no internal vibrations down to nanometers level. So this is experimental sort of capabilities part, but now I'm going to go back to the data and results. So these are typical images taken on one of the overdosed LSCO samples. We start with the lowest temperature, 5.6 Kelvin. You see this blue color, which corresponds to a fair amount of screening. Well, it's basically a perfect screening. And then you increase the temperature. This blue color doesn't change much as we change the color scale, but it actually goes down. And so you proceed, 9.4 Kelvin, 10, 10.5, and then 11.6, you still see some of the blue color. Then 12, you pretty much abruptly get a normal state. So the transition, the critical transition temperature width is about, as good as we can measure in our squid, which is, below 0.4 Kelvin. Our thermometer is not exactly on the sample, so there's some uncertainty, but these are very, very sharp transition temperatures, and the quality of the uniformity is very comparable to single crystals, and actually some of the non-uniformities, or most of them, actually come from the squid itself, from the way it moves, from the way it might be touching the sample. So actually, there are artifacts predominantly from the measurements themselves. And we've confirmed these observations on a number of the samples. And now, so the question, okay, so the images are uniform, but how do we make the quantitative conclusions? So to measure actually the penetration depth, which will go as 1 over the superfluid density, we do what we call approach curves, meaning we move the squid close or away from the sample, and we get this curve, for example, at the lowest temperature, where the strength of the signal gets negative, meaning more screening near the sample. And then we can fit these curves to this expression that includes the penetration depth, the distance dependence, and some other constants, and extract the penetration depth itself. And this model was introduced by Vladimir Kogan and also John Kirtley 10 or slightly more years ago. And so then we do this measurements, approach curves measurements at different temperatures at a specific location, but also we can repeat it at different locations. And so then you can plot for each location, you can plot, for example, the magnitude of the susceptibility, and it looks like that. Now, it's easy from now, after we do the fits, it's easy to translate the penetration depth to the superfluid stiffness, of course. These are just algebraic formulas. And here's what we get. So the data are shown by symbols. You have blue triangles, orange triangles, and red triangles. They all fall within the these two dashed lines or three gray lines that are taken from the bulk measurements, and essentially within the error bars of our experiment, which are shown here, we pretty much confirmed the linear dependence of the superfluid stiffness in basically an agreement with the bulk measurements. Now, I should say that the error bars are actually the relative, mostly relative mostly absolute penetration depth error bars, because the distance of the squid is not always well defined, but it's sort of reproducible error bar from one point to another. So whatever the relative penetration depth is really linear. That's what I'm trying to say here. So, and then you can basically say, well, this does agree with the Nature paper from 2016, and this is, just shows the power of local technique and how it can complement bulk measurements. Just to conclude, the samples were found to be quite homogeneous, and I was actually quite surprised to see that the landscape was quite homogeneous across the samples. And, really only variations that are beyond a few percent were coming from like scratches created by us, rather than anything happening in the samples intrinsically. This is, of course, happening on the micron scale, which is the relevant scale for the penetration depth. Now, for the future experiment, we can think about, and we're doing some of these experiments on other 2D materials, where, knowing the penetration depths is, of course, a fundamental thing you want to know for knowing pairing symmetries and things of that kind. So thank you for your attention.
So far you started with LSCO. Why this choice of this compound? Is just a question that something like experimentally said that it's the only sample you had, or is there some deeper reason?
Well, I mean, for the junctions part, the problem that may arise in junctions, if you get not very high quality junctions, you're just going to get leakage current. So LSCO junctions, basically are grown perfect, or films are basically grown, as perfectly as they can be by Ivan. So that's kind of the reason for the choice. But of course, there are deeper reasons. The reasons were to, like the original reasons for the junctions, I guess, were to see, some unusual tunneling features in LSCO, just to try and understand pairing mechanism based on maybe hunting after fine features in the tunneling spectra. But then it turned out to be, we basically discovered the noise part. And so it's not like we said, oh, yeah, we're going to see the noise, surely, and let's use LSCO. It was kind of the other way around. LSCO has some puzzles, of course, as a cuprate material, and we know we can grow them well. Ivan can grow them well. And so we were after doing really, really high precision tunneling spectroscopy originally, if that answers your question.
Can I ask a question?
Right.
Yeah, Megan?
So can you please show the measurement itself, please?
Which
you know,
part?
when you do the fit, the quasi-particle fit, and then you start to see pairs. Slide 4. Yep. So, I mean, for me, so this is LSCO. You have at which doping exactly? What is the doping, if you remember?
This one, I believe, is 0.10 or point.
It's underdoped. Around
this
10%.
is underdoped. Yeah, this is underdoped.
Around. So in 10%. I don't know if I understood it correctly, but at 70 Kelvin, you can clearly see that you have quasi-particles. Am I right?
70 is kind of hard to argue, but like...
No, quasi-particles, not Cooper pairs. Because you see, the shot noise will see which type of carriers you have. What
I
is
mean, there are some, at 70 Kelvin, there are some carriers that tunnel and they look like single electrons.
There is only them tunneling.
There's only them.
The only quasi-particles who are tunneling. And for me, that's kind of a nice message somehow. No? And then around 20, 30 Kelvin above, TC pairs start to appear. Am I right? And that's something which is kind of everywhere that way. Around 20, 30 Kelvin above TC, you start to see pairs appearing.
That's true. So yeah, this plot is actually, like I said, I like this plot more because then you can actually see this kind of delineated regions, and you kind of see this is 60 or 70 or something like that, and you still see these features here.
Yeah, sure. So I did look carefully through the data a little bit in the supplement, and first I was a little bit confused by the producibility of the junctions.
We measured at least 2 samples per doping, many junctions, but we reported 2 samples means 2 substrates per doping, but there are many devices on each substrate, and those devices on each substrate were also